Now let's explore exponential functions. What makes something an exponential function is when the variable is in the exponent. So let's just use x. The x is in the exponent. That's important because a lot of people think things like y equals x squared or y equals x to the third, that would be an exponential function because it's got an exponent in it. But as we've already seen, this is a quadratic because it's to the second power, and this is a cubic function because it's to the third power, cubed. And so it's not about x being in the base, it's about x being in the exponent that makes it an exponential function. To see the pattern or trend of these exponential functions, let's graph them. And I want to graph them in the most basic way so we can kind of algebraically see what's happening as well. And so what I want you to do is I just picked random x values. You can pick any x values you want, but when you're making a table and you're choosing the x value, sometimes it's good to have a couple of negatives and then a 0 and a couple of positives. So without using a calculator and just thinking about this for a minute, let's start with 0. If x was 0, this function would be 2 to the 0, which anything to the 0 power we've already seen is 1. And then if you go 2 to the first power, that would be just 2. And if you said x was 2, so you put 2 in the exponent, that gives you 4. Then let's go backwards and get 2 to the negative 1. Well, what a negative power does is it moves stuff from the 2 being on the top of a fraction. If you were to put it somewhere, now it's going to move to the bottom of a fraction, and the 1 power is going to stay on the 2 but lose the negative sign because it moved it. Then that's just 1 over 2 to the first power, which is just 1/2. Then similarly, the negative power moves this one down to the bottom of a fraction. You leave the 2 power on the 2, but the negative is what moved it down to the bottom of the fraction, and that's 1 over 2 to the second power, which is 1 over 4. Now let's look at one that has a smaller base, actually a base between 0 and 1. So 1/3 is a base between 0 and 1, and a unique thing happens here as far as how it turns out. This one's going to be a little harder to work. You can always punch these in your calculator, but I wanted you to think about what happens without doing that for a few minutes. So 1/3 base to a 0 power, if we plug in 0 for x, gives you 1. Just like anything to the 0 power gives you 1. And then 1/3 to the first power just gives you the 1/3. And 1/3 to the second power gives you, it's like 1/3 times 1/3 is the way you want to think of it. And you just multiply across the top. 1 times 1 is 1. Multiply across the bottom. 3 times 3 is 9. Or you can think of it as squaring the top and squaring the bottom separately. And then if we get into the negative exponent, we have to think of that carefully. -1 exponent. What that does is everything moves to the other side of the line, and that ends up being like a reciprocal, but I don't want you to think of negative exponents as being reciprocals because it just depends what the negative exponent is applying to. And in this case, the 1 that was being raised to the -1 power made it move to the bottom, and the 3 that was being raised to the 1 power moved it to the top. So it will always move to the other side of the line, top or bottom, and that's what the negative exponent does. Each of these were just to the 1 power, and that makes 3 over 1, which is just 3. Then on 1/3 to the -2, if you'll think of it as putting a -2 power on each of those individually, the top and the bottom, the 1 moves to the bottom with a 2 power on it, the 3 moves to the top with a 2 power on it, and then the top ends up being 9, and the bottom ends up being 1, so that's just a whole 9. Now you can see some similarities and differences. At some point on this one, before 1 you had fractions, and after 1 you had some whole numbers, and then here it was in reverse. You had before 1 you had whole numbers, and after 1 you had fractions. So they're definitely doing a different trend, but definitely not in the same direction, but they are a similar trend in that fractions are on one side of 1 and whole numbers are on the other side of 1. So let's see how that plays out in a graph. We're going to take these ordered pairs and graph them on a graph. First, in red, I'm going to graph the y equals 2 to the x power. So going through our table, what we ended up having is that when x is -2, y is -1/4. Now that's very, very close to 0, so it's kind of hard to show the difference. But that's about where it is. Then -1 is up at 1/2, so it's a little higher than the other one. And then at 0, when x is 0, y is 1. And when x is 1, y was 2. And when x is 2, y was 4. Now let's think about, we might be able to fit one more. Let's think about what happens when you put 3 in for x. So if I took this function and put 2 to the 3rd power, well, when x is 3, then that would be 2 times 2 times 2, which is 8. So 3, 8 would be our next point. So you can see the trend now of what's kind of happening here. The points are closer together at the beginning. They're more spread apart at the end. And this is actually called exponential growth when it does this kind of trend. So let me draw a line through these points, or a curve through these points. So here's my sketch through those points, the best I could do by hand. And so what's happening here is you always read graphs from left to right. So if you think about how it's going, from the left end, it's getting bigger and bigger and bigger and bigger, and then it just shoots up after a little while. And so that is called exponential growth, because it's not just growing at a steady rate like a line would. Linear growth would be like this, and it just grows at a steady rate, and it just keeps growing little by little. But the exponential growth will grow slowly at first, but then it'll shoot up really fast. Now we're going to show what the other graph looked like by plotting the points from the table. It was 1/3 is the base, x is the exponent. So let's plot these points. So at -2, we had 9. So it's way up there from the very beginning. And then at -1, we had 3. Then at 0, we had 1. It's the same spot that we had the other one. And then at 1, we had 1/3. So it's going to be hard to be accurate, but somewhere around there. And then at 2, we go all the way down to 1/9, which is teeny tiny. So it's going to be even harder to show that one, but it's really, really close to 1. So as you go out further and further to the right, those dots will come closer and closer and closer and closer to the x-axis. And so it's just going to get smaller and smaller and smaller and smaller. But just know it's actually never going to cross the x-axis. It's just going to get smaller and smaller and smaller, because think about if we had 1/3 to the 10th. Well, that would be still 1 on the top, because 1 to the 10th is still 1. And then 3 to the 10th is going to be some enormous number. And if it's 3 to the 10th on the denominator, that's going to be really, really close to 0, and so it's going to be really, really close to the x-axis. But the reason it will never cross below the x-axis is because no power is going to cause something to become negative that wasn't negative to begin with. So there's no power that will cause 1/3 to go negative all of a sudden. So let me attempt to make a curve through the blue points now. So as this graph, reading from left to right, if we ride this curve, we are going downhill at a very steep rate. But then the decreasing kind of tapers off as it gets towards the right. And so it's a quick drop, and then it gradually decreases little by little after that. That actually is called exponential decay. In finances, it's called depreciation, those kinds of things. And in the next lesson, we'll learn about applying these two different kind of exponential growth and exponential decay graphs to real-world situations. The last thing I want you to notice on this graph is that the place that the line or that the curve is getting very, very close to but never crossing over is called the asymptote. It's asymptote and then tote. The asymptote is any line that a graph is approaching, but it'll never cross over or touch, and so it just keeps getting closer and closer and closer to that asymptote. As you move this way, the blue line gets closer and closer and closer to the x-axis, and the red line, as it moves towards negative infinity, gets closer and closer and closer to the x-axis, but neither one of them will ever cross over that asymptote. In this particular case, the asymptote is y = 0, which is the equation of a horizontal line that's going through 0. And that is typical for your what we call our parent functions of our exponential functions. They will never cross over the x-axis or y = 0, and that is called an asymptote. It's an imaginary line. You don't always have to draw it, but just know if they ask what the asymptote is, that you put y = 0.